This is an example of the central limit theory, small application of its approximation. So a special weighted die will land on a 6 22% of the time. Now it's only supposed to land on it 1/6 of the time, which is a little bit smaller than 22%. So we're going to take this die and we're going to find the probability that it'll land on a 6 more than 15 times when rolled 50 times. So the way we're going to set this up is to start off with the formula for the central limit theory, which says that the standard deviation is equal to the square root of the probability times its complement. That's what 100 minus p represents. And all these numbers are in percents, so don't be changing percents into decimals for this formula, divided by how many times you're going to do the experiment. So if you're a company, then what you're doing here is testing out your product to see if it satisfies your constraints. All right, so the probability here is this 22%. This is the constant probability that this thing is supposed to land on a 6, also known as experimental. Down here, this 15 times rolled, 15 land on a 6 15 times when rolled 50 times is also a probability, but it's a specific one. So this one would be considered X bar because it's the one that generally happens theoretically, and then this 15 out of 50 is going to be the X in our statistics. It's the instant data value. All right. So we're going to start off with sigma is equal to the square root of p, which is 22, times 100 minus 22, all divided by how many times we're going to do it, which is 50. So this is the standard deviation based on the mean of this experiment. So we're going to get the square root of this value. So on a calculator, I would put the square root in first, so second x squared, and then just type it in, 22 parentheses 100 minus 22 end parentheses divided by 50. And the calculator tells you that the answer is 5.86. I'll put it in 2 decimal places. Whoops, wrong end. Whew. 5.86. Okay, so then the rest of it is we want to know what's the probability that it'll go more. We're going to do a z-score. So x minus x bar over sigma. So we're going to get z is equal to, now x in this case is the data value, 15 out of 100. So 15 divided by 50 is 0.3, so that would be 30%, minus 22%. These are all percent, so I'm just going to do a simple leave them all in percent form. This is also, a percent down here. 5.86% is the standard deviation. All right, so when we do our z-score here, we're going to get 30 minus 22, better known as 8, divided by 5.86. So our z-score is 1. If we use the table, it's 4. But it's 1.365. Or if I do a spreadsheet version of this, it would actually take all the decimals. All right, so we look up 1.4 on the table. So 1.4 on the table is 9192. So this becomes 9192%. 1.4, 9192. Okay. The problem is, when we're doing this normal curve, it's going to be ugly. We're looking at, here's 0, 1.4 is someplace over here. And the thing that usually messes people up is they look at the number on the table, they think that's the answer, and they'll plug it in. But this says more than. So when we're talking about more than in the picture, we're talking about this part of the graph, the top end. But percentiles only work towards the left. So the final answer is going to have to be the 100%, the whole curve, minus that bottom part to give us our top part. So this would be 100 minus 91.92 for a grand total of 8.08% of the time. So it's a very small chance that this thing is going to land on a 6 more than 15 times when rolled 50 times. It's a very, very small chance. More than likely it's going to be less, 91.92% of the time. So this is what the central limit theory does. It doesn't allow you to get too far away from the mean of 22%. The farther you get away from it, the harder it becomes to get that far away from it. In other words, it keeps your answers pulled to the center. All right, so that's the central limit theory.